to share his insights about his present publication into this area, so that we all can have an exchange of his knowledge. Also, I would request all participants to make it engaging session, so that we can have more fruitful knowledge exchange between us and between Dr. Boniface. So, over to you, Dr. Boniface.
Yes, good afternoon, all over the world, different continents, and I really much appreciate it to those who have managed to attend. I really very much impressed by the invitation from Dr.
Excuse
Abhishek
me,
Gupta.
Doctor. May I request you to please switch on your webcam to make it more interactive? Sorry to interrupt you.
Just come again.
Can you please switch on your webcam to make it more engaging and interactive session? Thank you. Thanks a lot.
Yeah, so I was just greeting all of the red every continent where someone who have managed to attend for this webinar, especially for this particular topic that we may discuss about. And I really appreciate everyone who have managed to join. So you will allow me to share my screen so that you can discuss something which is very interesting for the area either of research and also in terms of power system. So I think everyone is clear by looking at my screen. Yes, from the audience, I think everyone is seeing my screen.
Yes, it's pretty much visible.
So may I proceed?
Please, please. Thank you.
Okay, thank you very much. So my name is Boniface NTAMBRA. Actually, I'm currently a lecturer expert from one of the that are holding the engineers in the field of mechanical engineering, another fields such as IT, and also I have also a researcher from the European Union for the battery management and for focusing on zero waste and zero waste digital manufacturing, so that to manage improving the efficiency of the system when it comes to make a zero waste. So I conducted my bachelor in electrical engineering from Rwanda. I did my first master's in Republic of Kenya, and I have graduated in 2022. I also did my second master's from embedded systems. I'm currently working as scholar in Rwanda, especially for cyber attack defense through using artificial intelligence and combined with Internet of Things and blockchain technology. Where also I'm conducting another research related to the battery management from Jomo Kenyatta University in Kenya. Yeah. So actually, what I want to say, I'm a researcher. When, for example, you may try to see my profile clearly in a simple way, we can normally go to Google Scholar. I think you will get all my details. So you type my names, Boniface NTAMBRA. Then we normally scroll all the publications or the research work that they have normally managed to publish. And I think everyone should be aware on what's going through publications. What I may just focus is that when you try to make publications, you are engaging, or try to link academic barriers through providing solution, so that maybe some industries can get the solution from the academic. That's what you may be able to get interested. Yeah. So by continuing, so this research that you want to make the webinar, it was published, it was submitted to Spring Natural Applied Science. This is a normally common worldwide publisher that has an impact factor very high, even the index. It was submitted in 2021, December, and it got accepted and published in 2022. So it is about Rwanda power system protection in cascading event and in power blackout. So I'm the main author, but it was with a lady called Umhoza, who is now working as a division manager of e-payment in Rwanda Information Science Board. So when we talk about the optimization, some engineers can think what things to optimize when you come to different areas of power system. For example, if you deal with a power system protection, either in cascaded events or in power blackout, so you need to know which parameter you may optimize, either to assist in protecting your network. For example, in Rwanda, we normally have a network, a grid, which almost about 500 megawatts as production, but also as you keep increasing demand increase, so we need sometimes to protect our network so that we can prevent any power blackout or any event that can harm the network to not function as normal. So once we really deal with optimization, normally on this research, I have tried to focus on optimizing the frequency, which normally here in Africa, we normally have a 50 hertz, but which may be plus or minus 5%. So this means that it can be beyond 50, but not beyond, not below 848, also not beyond 52 hertz. So from the case of Rwanda power systems, that's what I want to make optimization, is that I wanted to deal with frequency, as long as the power blackouts may occur, but in terms of imbalance between the loads, so that the system itself can adapt to the changing of load. So actually, I have also dealt according to the how comes when your power network become disturbed, either it is overloaded or underload. So these two cases, it happens if the power system is beyond the required, which means that it is overloaded or it is underload. So this means that the frequency should be getting affected. So this can disrupt the network operation, which may require some engineer to take action. For example, let me say the current power network was based on a single area power generation, which is existed using an adaptive control called PID, proportional, integral, and derivative, which is a scheme used to control this single area power network power generation, but it was just based on hydropower, where, for example, we have a generator connected with a turbine. So this generator normally fed the input to the turbine, where the turbine should be added to this so-called generator. But one here, you need to have a feedback, which is a frequency sensor, to sense if the output is being checked or is being corresponding to the input. So this will be able to have here a comparator to compare if what you are expecting to the output is normally what you will gonna to compare according to the difference. For example, we have taken an example that maybe we suppose we have a 250 megawatts, which is being fed to the governor to give a signal to the turbine, either to feed for this generator to know what will be the output. So, for example, here all the models, these are a frequency change in power units, where you can be able to display all the frequency behavior. So normally the current single area power generation that we experience here in Rwanda, and this normally based on different regions. For example, when you go to Western region where you was dealing with this power generation for the single area, so you find this normal control scheme is happening. So from this research, we also considered the two-area network, where we have a single area generation combined with the second area generation. So this is like we have like a wind power plant or hydro power plant, which is going to be connected together with solar power generation. So we have two different area network, area generation, which is being connected so that we can be able to feed the load. So this means that we may be able to take all the controls from either load reference one, then we connect to the comparator. Once we get the output, it has to come to compare according to what the load reference. For example, if we have the output like 200 megawatts, so this means that
Excuse me.
Yes.
Sorry to interrupt. Can we have a little larger screen? It's very small and not able to see it clearly, the blocks. Can you please zoom it?
Let me try.
Thank you. Yes, it's better now. Thank you.
Oh, okay. So I was saying that when it comes to power area network, this means that you are connecting two generation together. I was giving an example, like if you have like a solar power generation, then you want to connect together with hydropower, which is going to be fed on the same network. So this means that you need to have a two-area connection, so that you can transmit these two outputs to the grid. So here, what we normally see, it's like a closed loop, where each area generation contains to the frequency sensor to see if the output is matching to the load reference. So this means that if we get like 200 megawatts at the output, so these sensors come to compare what is within the reference, and then this is what you feed here. Then you add the controller, which called PID, so that it can check what are the output from the turbine, so that it can generate a control signal according to the output. So all of this now we come to fed through this mix. This mix it was considered like a busbar, which can receive two power, so that you can be able to measure the frequency at the end of the output. So this one should be able, these blocks should be able either to simulate how new frequency and the frequency change is look like. So we keep reminding that this frequency change will determine if our load is being disturbed, or if either it is under load or it is overload. So here, that's what we have dealt with. So now let's bring now a solution where, from my research, I have proposed to use a power system automation stabilizer to make sure that at least once the load is unexpected, so that the system should balance the frequency itself. For example, let's come to single area network. To single area network, where I have proposed this power system PES-IAS circuit, which is a block developed by myself to check if this power automatic stabilizer gain is matching from what is expecting from the output when the system is single area network. So of course it's the same, but here the role of this is normally to balance what comes from the output and comparing to the input. Then the system for this PSS circuit should get what we may call like a control signal to balance. If the if the frequency increase, then the balance of the load should be maintained and should be controlled. So normally, allow me to share what is the components made by this power system automatic stabilizer circuit. Allow me also to take you. This is a research that I want to share with you. For example, for example, when we see this is the automation stabilizer circuit. This one, where we normally have what we call a washout. So this we balance, for example, we check the speed of the inlet. For example, let me say the flow is water, maybe we consider like an hydropower. Where this water washout, we just check what are you feeding within the turbine. As you have a sensor that has sense either from the output, what is going to be the output, then you need to have this sensor in order to detect what is supposed to be getting like an output. And then here we normally have what we call rag grid compensator, which will work like a filter, either to filter some or the unwanted signals from the circuit. So normally these are the kind of filter that is just it's slow to either to reduce the signals. I mean to reduce the signal, or maybe to remove unwanted noise within our network. So just here I wanted to show you what is there within this power system stabilizer, automation stabilizer control circuit. So now we back to the circuit. We back to the circuit. So this normally when you try to create a subsystem from that particular control circuit, now you get one input and a single output. So once you get now so please remember that normally key PSS considered as a sensor, it's normally now considered like a gain. So this normally particular a block that you may be finding from MATLAB, because all these block diagrams was modeled and designed in MATLAB, so that you can be able to get to get the meaning of this particular sentence. So, and then you keep come here to see what normally we wanted to generate as an output. Then what you know now, you really want to consider to measure the frequency, because frequency imbalance should be determined either if the load, when it is overloaded or when it is underloaded. Another thing is so now we come where we may propose also the generator control when it comes to two-area power generation. So as we keep reminding, is that when you have two-area generation, so of course you need to have a two different control, but maybe you may find they are sharing the same parameter control, or maybe they are sharing the same control strategy. So here, what also we did, we take that particular power system automation stabilizer, we normally connect in series with that power stabilizer gain, because now they integrate from the output, and then it comes again to compare within the input. The same case, it comes to the second area generation, where all of these control circuits should be in parallel with the previous area control, which are being based on PID. So then all of this control can be able to help to stabilize what is coming from as load references and what is expecting to get as output. And then here what normally I did, as you get the frequency as a parameter you need to optimize, now I have be able to manage to create what is the converter from either frequency to megawatts. So normally in power systems, this conversion, sometimes you find it is high, or somehow impossible. But what I really want to tell you is that there is a control model. Let's also share what is here from frequency to megawatts. And also, we also have a resistance inductor load, which normally the kind of load we really normally have here in Rwanda. And maybe this formation of kind of load may be shared to other people, maybe in East Africa or in Africa. But what I want to say is that once we normally have a frequency as controlling an optimization parameter, we may be able to change using some control models within MATLAB. For example, let me also share, as we here. So, for example, let's see this frequency to megawatts. So it's like I have an input as hertz, which is unit of frequency, but I want to get output of megawatts, which units of power. So what I did, normally you have to integrate so that you can change from one meaning either to other meaning by integration. This is sometimes a control model that you find in MATLAB. Once you integrate the frequency, normally you may be able to get the control unit power, which is megawatts. Then here you need to have what we call a power frequency measurement, which is a gain for conversion. It's like here a converter. Then you also after you get the megawatts, because as we really need to convert either from megawatts to frequency, so we're going to have also another bring back a power frequency module, which will helping also to measure the frequency at the end. Then this is how we normally design it and model the LR load, which is being utilized as a kind of load which may be either changed or whatever. So now we're back. Now we see where we came from. So of course we have created two subsystems which may be able to like a frequency power measurement. Then we have a connected load. The things here again, I have created any sudden load. So in the power system, normally this sudden load, we may assume that either there is an industry which can consume, let me assume that 1 gigawatts or 1 megawatts to be added randomly on the power network. So we don't need just to go and reset, except this system can be checking itself what are the load you want to disturb your network. Or maybe people are connecting the motors, are connecting the generators, are putting their systems or whatever. But what here to do is that even if this sudden load can be unexpected, but won't affect the network, as long as you have the control model of all of these two area power generation. And then we measure also the frequency. Either we get what's the new frequency, nominal frequency, and what's the new frequency. Then you can be able to see what frequency change, which may affect, to see if either the load affects the network. So allow me to share what is the expected output once we normally deploy these PSS circuits 1 and 2, either when you are on a single area network or when you are on 2 power generation. For example, you remember our network currently somewhere they are using some PID control. So this PID control, there are some output frequencies when you try to simulate the model created using MATLAB. So now, for example, if you simulate, you find now once the load disturbs the network, the frequency at initially from 0 seconds, it starts by 50. But when it reaches to the 1 second, now the fluctuation comes where now the frequency dumped down to either 49.91. So now you see the frequency become disturbed, but the disturbance resisted till to the 10th second. In the power network, if this disturbance is appearing within your network, so this means that you may experience a power loss, either out of even to 2 megawatts, which is a bigger loss, for example, to the developing countries such as Rwanda. That's why we have implemented to control immediately after it comes to the system of controlling. So now this is what it has been existed. So for the first graph on C, so this shows that once the load is increasing to the greater than the demand, I mean, once the demand is greater than the generation, so you normally experience some higher frequency. I mean, to this point D, some higher frequency. But this means that the overshoot is high. So now when it comes to once the demand either is less than the generation, now you see how the disturbances within the frequency, how it was looking like. So the aim of doing this is just to know that either if you are planning to have a network, so you need first of all to plan what are the demand. And even it's very nice if you can think beyond, and then you expect if maybe at the end of the day, you're going to have either a greater demand than the generation. So that's why you need to control the frequency, because it may disturb much, and then you lose in terms of cost, in terms of trust and reputation, it may be dead. Then when you see from A and B, we compare, for example, the proposed PID PSS control. So now I have be able to connect my developed control circuit PSS, then together with the PID. So when the disturbance came, you see the disturbance appear in 1 second, in 0 second, but within 0.2, now the disturbance is clear, is being cleared from the network. So this shows that the developed PSS control combined with PID, it has a good enhancement and good accuracy when you consider to this existing PID control. So that's why it is preferred to use this this control, the one I have developed, so that because it detects very minimum microsecond. Once the disturbances appear within the network, then it should be cleared within 0.2 seconds. While here, it may be cleared within 10 seconds, which can be able to cause some losses, some energy loss and power loss. So the same once the demand either is greater than the, is below the generation. So now you can experience a higher frequency, but this higher frequency comes within seconds, but within like 20 microseconds or 0.2 seconds, now the disturbance is being cleared. So this clearance shows that how this developed PSS control should affect in a good way and have an impact within this control network. Another thing is, okay, this is for single area network. So now let's come to the two area network. So you see how the frequency, even the disturbance can remain within industry are being dead. So means that here in Rwanda normally once your network disturbing the customer, where they can experience some losses of their systems, such as maybe there are short circuit of the machines, the generators, whatever, or other load connected. So we need to deal with them. Why these networks have been enabled, disabled to provide a good power. So once now the disturbance remain within the network in 20 seconds, now you can experience a lot of megawatt loss plus penalties that you need to pay to the customers. So once you have a two-area generation, so the same case, you control my proposed and developed system. You see now it has a good control mechanism, because the disturbance may occur within 0 seconds. So within 0.2 seconds or 0.1 second, it's clearly automatically. So this means that my developed network has a good enhancement and a good performance. So the same case, once you want to have a greater demand, greater generation than the demand. So now you see even the disturbance may be cleared within 20 seconds, but when it comes to the control strategy, normally you use maybe within 0.3 or 2. Now of the power frequency, the frequency within a shortened time. So this means that my developed system provide a good impact on the network. So I may recommend that even among you, if you may have experienced it with such kind of power disturbances. Maybe this control strategy can assist to stabilize your network. So I may normally want to conclude. This is normally the performance that I have been able to measure, where that the system we experience a very good performance when it comes to overshoot, and when it comes to steady state frequency error, and when it comes to the settling time. So the settling time actually it comes within a very minimum second. Once also in terms of overshoot, so we can experience a very few 0 point something frequency change. So this shows that the developed system control strategy, so it has a higher performance when you consider to the existing control strategies to the network. So I can say thank you for attending. So I may welcome the session of question and answer, and may God bless you. Thank you very much.
Thank you, Doctor. It was a very nice session and very informative. Alongside this, I was going through this session, and a question which I uh, can see is very much significant to all of us is that we can see it is very fast to solve the overshoot and solve the error into the power system. The controller acted very fast. The response time is very less. So, what makes it more challenging in terms of the load disturbance, so that we can make it more efficient to make it more fast responsive?
Yes, come again. I am not hearing well.
Let me repeat. The response time of your controlling system is very good. It is settling the overshoot very quickly in microseconds. It is settling. So, what is the limit of this system so that our system needs further enhancement?
Uh, the foreign instrument that you may be able to make. For example, for here myself, I consider when the load maybe is greater than either the generation, or the demand is greater than the generation. But here for further enhancement, we may be able to include either other control strategies, because these load disturbances may be a really load. But sometimes you can find the network can be disturbed by either issue of cyber attack, which can be able to change either the demand. So now this system, it can have some challenging if it comes to the cyber attacks in terms of the load change, when a cyber attacker could be able to modify either the load demand or load degeneration. So more control strategy advancements is very recommended when it comes to the cyber attack issue.
Okay, so basically, uncertainties into the load generation or power generation, these should be tackled with more subsequent robust control strategy, right?
Yes, right.
That's great. Thank you. Thanks from my side. Also, I would request to our participants to take actively participation into discussion so that we can take the maximum benefit from his knowledge and his research experience.
Is power cable, power cable.
I see, Mr. Boniface, our participants are right now not having questions. Later on, they might share the questions on to the email or onto the WhatsApp group. And in that case, I would request you to please answer as per your convenient time to their queries.
Yeah, we surely may all the questions may be welcomed either through WhatsApp group or maybe my email. so that I can be able to answer in cooperation with all of you guys.
Sure. And if anyone from our participants want to collaborate with Mr. Boniface in their research and want to have a personal discussion session, then they can schedule the meeting from our Scholars Collab profile, Scholars Collab platform with Mr. Boniface, and we will schedule the meeting with him if you want for to discuss your research issues or to discuss or to collaborate on to the common research area. All right. So I would like to thank and want to wrap up this meeting with Mr. Boniface. And on to the behalf of everyone, I would like to thank you, Mr. Boniface, about your time and your research experience. It was very nice, engaging session. And looking at this research, it is very much prominent and to very enthusiastic to see like how research into power system blackouts is going on. So again, once again, I would like to thank you for your time. And if there would be any other collaboration request from anyone, I would be happy to share with that with you.
Yeah, thank you very much, and being welcome to everyone for each and everything Church may share, and then we'll be able to discuss a little bit on that.
Thank you, everyone. Have a nice day. And please don't forget to mark the attendance also so that we can generate the certificate too. Thank you. Thanks. Thank you,
Yeah,
everyone.
Thank you very much.
thank you very much.
Thank you.
Thank you.
Thank you.
ubwo twanzuye ko muzakora muziga kuri nusi cyasi ni utubazo dukeya within 2 hours or 1 hour and a half. Mwebwe muhitemo aho muziga tu. Ya mbere assignment. So ubwo no kuvuga ngo we will meet again on Monday. Yes. Sapire nababwira. Kandi mwazi nyine mwazi sizo se nyine. Yezo ngizo mwazi. Ya mbere ya kabiri. Guidance wana guidance na. Azeni ayo ni mani bichana. So you will study this learning outcome, but you have to focus on this rate of discharge. So focus here, only here. Are you together? So this learning outcome why not heat and mass transfer? So okay, take care on this learning outcome, focus on this. Are you together? Then let's skip learning outcome 2, but come to the learning outcome 3. So focus focus on heat transfer mode. Heat transfer mode, and even some heat exchange. No. Focus on this. This is only the one we deal with. Cut. These are only photo. Wait. So make sure you read and understand just a simple calculation, like drinking hot tea. So this is and this is. So other things like conservation of mass industry, manufacturing process, you can be able to read. So all of the things here you can be able to read. Even I come with thermodynamics, those who deal with property, thermodynamic law, even application in air conditioning and refrigeration. Ni bande bakoze ibi ngibi ya air conditioning, thermodynamic law ni ya kabiri, air conditioning, working principle, types. The people who have said something about boilers. So I think some of the things here you have seen through your presentation. Silvio? Okay, maybe we'll take some session to see what's there. Okay. So ukani nyine byarangiye. Muyashake sha. Okay, I will share something. There is a document I will share with you, but I don't know where it is. You know, some of the document I have lost it. There's something I have lost. I don't know where I put my documents. I will check, but once I will check, keep read on where we are focused. So I'm going to share with you this PPT. I will share with this PPT, the one we have what we have seen this night. Then you will be able to read, and there is some exercise you may be able to perform while you keep. Okay. Any question? So I think now we are done. So I have tried as much as possible to see the way things may be done nicely.